Section: Introduction. In this section, we explore how representations change during task learning, a key question in neuroscience and machine learning. While learning dynamics are commonly studied, the changes in representations after achieving high performance on a task are less understood. Recently, we have seen the grokking phenomenon in deep learning, where neural networks first achieve high accuracy on training data and then, after extensive training, suddenly generalize to new data. This unexpected behavior has drawn significant attention, with various theories suggesting that grokking results from factors like weight decay and initialization norms. In psychology, there is extensive research on learning across different expertise levels, particularly how experts continue to learn even after mastering a task. However, experimental neuroscience lacks a clear understanding of learning dynamics during overtraining due to challenges in testing whether representations evolve during this phase. For instance, recording neural activity in animals can be invasive, often limiting observations to the end of training. Additionally, neuroscience experiments typically do not structure stimuli as training and testing sets like in deep learning, making it difficult to draw conclusions about learning and generalization. We focus on a study that examines neural activity in mice trained to distinguish a target odor from many non-target odors. After reaching mastery, the mice continue training for weeks, during which we record their neural firing rates. We observe two key phenomena. The accuracy of decoding training labels from neural activity improves during overtraining, even though the mice's behavior does not change, and those that undergo longer overtraining perform better on new test examples afterward. Our aim is to understand the representational dynamics in the cortex that underlie these observations and to see how they compare to those in deep neural networks, where learning continues after reaching peak accuracy. We find that the representations of target and non-target odors in the mouse cortex continue to differentiate during overtraining, resembling the hidden progress seen in deep learning. We also observe that the margin of the maximum margin classifier increases during overtraining, indicating that some odor trials that were misclassified at the start may be correctly classified later, despite unchanged behavior. We develop a synthetic model of the piriform cortex that captures these dynamics and the grokking phenomenon. This model helps us understand the learning process as one of maximizing the margin. We propose a new explanation for the overtraining reversal effect, where animals that are overtrained learn task reversals more quickly. Our findings align with previous observations of sharpening in learned odor representations, suggesting that these phenomena are robust in the context of mouse olfaction. We acknowledge that our data analysis is observational and outline its limitations, while also providing experimental proposals for testing our hypotheses. In discussing related work, we frame our ideas within the concepts of lazy and rich learning in representation learning, which have gained traction in computational neuroscience. Lazy learning refers to a trained network being well approximated by a kernel method initially, while rich learning occurs as the network learns relevant features and moves away from its initial state. Margin maximization is a form of rich learning, defined as the distance from the decision boundary to the nearest data point. We also review the theoretical work on grokking, where task-specific learning happens long after training accuracy has plateaued. Various theories explain grokking, suggesting it may be due to factors like weight initialization or competition between memorization and generalization. Recent studies support the idea that rich learning often manifests as margin maximization during overtraining, with evidence showing that this process can lead to grokking in certain tasks. Section Summary. In this section, we explore how representations in the mouse piriform cortex evolve during overtraining on an odor discrimination task, revealing that neural activity continues to refine despite unchanged behavior, akin to the hidden progress seen in deep learning. We also connect our findings to the grokking phenomenon, suggesting that margin maximization plays a crucial role in this representational dynamics. Section: Revisiting neural data from overtraining. In this section, we revisit neural data collected from the posterior piriform cortex of adult mice during overtraining on a binary odor discrimination task. The posterior piriform cortex is crucial for processing smells. We define an odor as a specific combination of 3 odorants within a set of 13. The mice are trained to distinguish between a target odor, which contains these 3 specific odorants, and non-target odors, which do not. After an initial training phase of 8 days, the mice achieve high performance, but we continue training for an additional 18 days, during which we record their neural firing rates. We analyze the population firing rate matrix, which captures the neural responses for each trial across multiple days. With around 200 trials per day and about 15 neurons recorded, we find that the representations of target and non-target odors become increasingly distinct during overtraining. We visualize this separation by plotting representational similarity matrices at the start and end of the overtraining period. This analysis shows that even without changes in behavior, the mice's brains continue to learn and refine their representations of odors, which may help them generalize to new, unseen odors. Next, we explore how these changes in representation improve the performance of a maximum margin classifier, a concept from statistical learning theory that measures confidence in predictions. We distinguish between 2 types of margin maximization. One where the classifier improves simply by training longer on the same features, and another where the features themselves become more aligned with the task. We focus on the latter, where improvements in the features lead to better classification. We track the distance from the classifier to the closest examples, finding that this distance increases during overtraining. This suggests that the representations in the posterior piriform cortex evolve to enhance the classifier's margin, similar to findings in deep learning where networks improve their performance by maximizing margin. We note that since we do not have test data during training, we cannot determine if the initial representations are rich or lazy, which is a limitation of our analysis. However, it is possible that some inherent bias towards generalization helps the overtrained mice learn useful representations for challenging examples rather than simply memorizing their training odors. Section Summary. In this section, we analyze neural data from mice trained on an odor discrimination task, revealing that even after achieving peak performance, their brain representations continue to evolve, enhancing the separation between target and non-target odors during overtraining. We also demonstrate that this ongoing representation learning improves the robustness of a maximum margin classifier, suggesting that the neural representations are optimized for generalization to unseen odors. Section: A synthetic model of mouse piriform cortex. In this section, we construct a synthetic model to study how mice discriminate odors, adhering to biological principles. We know that the piriform cortex receives input from mouse glomerular channels in a random and scattered way. We define odors as vectors that represent different chemicals, which we then process through a random projection, reflecting the role of glomeruli. We train a multilayer perceptron, MLP, with one hidden layer to identify a specific target odor from a set of 200 non-target odors. To simulate realistic firing rates, we use a ReLU activation function. We also set aside 20 test examples that share one chemical with the target, making them more challenging to distinguish. We train the MLP using standard gradient descent on a cross-entropy loss function. The behavior of the mice and the neural activity are modeled by an overtrained MLP, which mimics the mouse's responses. Interestingly, while the training loss stabilizes at a low level, the test loss continues to decrease for many epochs, indicating that the classifier is improving its ability to differentiate between the target and non-target odors. We observe that the representations of the target and non-target odors begin to separate during training, but they are not easily distinguishable even after extensive training. Notably, overtraining on the task of separating target and non-target odors enhances performance on the test odors, which were not included in the training. This improvement occurs because the network focuses on maximizing the margin between these representations during the overtraining phase. We see a significant increase in test accuracy during this period, particularly between epochs 1000 and 9000. To explore feature learning, we increase the complexity of the odor vectors and the number of overlapping odors in the probe trials, which allows us to assess varying levels of difficulty. Although our model is not trained on the probes, we monitor their accuracy to understand how maximizing the margin on non-target odors aids in tackling more complex trials. We track the Fisher discriminant, which helps us measure how well we can separate the target and probe classes throughout training. This statistical measure indicates the best direction in feature space for distinguishing between the two classes. We also consider potential biological factors that might influence late-stage learning. Certain loss functions in deep learning have been shown to promote late-time margin maximization, and we speculate on biological mechanisms that could play a similar role. One possibility is the energetic and metabolic constraints faced by biological organisms, which may lead to various neural behaviors. These constraints can encourage neural networks to focus on relevant tasks rather than adopting a lazy approach. Another factor could be the occasional errors made by the mice, which might provide a small supervised signal that drives late learning. Additionally, we propose that unsupervised components in the learning objective could penalize low-confidence predictions, guiding the learning process even when predictions are correct. This ongoing uncertainty in predictions could help maintain feature learning during periods of overtraining, as seen in rodent brains. Section Summary. In this section, we construct a synthetic model of the mouse piriform cortex to simulate odor discrimination tasks, training a multilayer perceptron to classify target odors while observing the emergence of separable representations during overtraining. We also explore potential biological drivers of late-time learning, such as energetic constraints and the role of uncertainty in predictions, which may facilitate continued feature learning even after training accuracy has plateaued. Section. Rich learning during overtraining can explain overtraining reversal. In this section, we explore whether our model of learning dynamics during overtraining can make predictions beyond our immediate context. One clear prediction is that late-stage feature learning leads to quicker adaptation when tasks are reversed. In machine learning terms, this means that a predictor can quickly adjust when the output changes from a function to its negative. If a network has learned features to compute a function, many of those features can be reused for its negative. However, this does not hold if the network learns the function in a lazy manner, where the initial features are not specific to the task and cannot be effectively repurposed. While this prediction may seem tailored to a machine learning audience, overtraining reversal has been studied by experimental psychologists for many years. Theoretical insights in psychology suggest that attention allocation plays a role, and our model provides a more detailed neural framework for understanding overtraining reversal, which we believe is unique. We define the overtraining reversal effect as the observation that animals overtrained on a task adapt more quickly when the task is reversed. Specifically, when animals face a perceptual discrimination problem and the reward mapping is flipped, those that were overtrained adapt in fewer trials compared to those who were not. We offer a straightforward explanation for this effect through the lens of feature learning. Our argument hinges on the idea that better features lead to easier task reversal. We compare a model that has been overtrained to one that has just been initialized randomly, noting that the overtrained model has features that are more aligned with the task. We assert that a model pre-trained on a function will learn its reversal faster than a randomly initialized model because it has features that are better aligned with the task. We denote the hidden representations of a neural network trained to learn a function as phi, x. When training the readout weights on the reversed task, we can use either the pre-trained features or the initial random features. It is known that feature learning increases alignment between the final feature representation and the target function. We can express this alignment mathematically, and if both the original and pre-trained features align well with the target, we can establish a condition that shows improved task model alignment. Empirical studies have shown that feature learning enhances this alignment in multilayer neural networks. This concept captures the idea that feature learning allows a network to adapt its weights to relevant directions, leading to better generalization compared to lazy training. When we train on the reversed task using mean-squared error loss, we see that using pre-trained features improves the convergence rate compared to using original features. The key insight is that if features are well aligned with the task, we only need to adjust the readouts rather than retrain everything from scratch. To illustrate this advantage, we revisit our synthetic model of the piriform cortex. We train our model on the original task until convergence, then reverse the task labels. We find that the model pre-trained on the original task learns the inverted task more quickly than a randomly initialized model, which struggles to achieve low test error if we only train its readouts. This aligns with the reversal effect observed in experimental psychology, suggesting that overtrained animals have better task model alignment and richer features, allowing them to adapt to task reversals more efficiently.